Hi, I'm Michael Chang, and on behalf of my co-author, Sid Kaushik, and advisors Sergey, Levine, and Tom Griffiths, I will present our work, Modularity in Reinforcement Learning, via algorithmic independence and credit assignment. You are in the burrito business, and you make some world-class burritos. Your team is trained to follow this policy. First, you heat the tortilla. Then you add the vegetables, and last, you add the meat. Things are going great until this week. This week, the meat was contaminated from the meat supplier. Customers got sick and gave you a lot of angry reviews. Continuing with the optimal policy from before will only make things worse. Clearly, credit assignment should modify the decision of adding meat and perhaps replacing it with tofu. But how should we perform credit assignment on other decisions from the same decision sequence? Intuitively, nothing. We should be isolating credit assignment only to the last step without affecting anything else. The key intuition here is that if we have a modular way to perform credit assignment, such that it is possible to modify one component without simultaneously modifying others, then the system could more efficiently adapt to new contexts that have not been anticipated before. Unfortunately, popular learning algorithms do not seem to do a good job at this. Here's the same scenario represented as a transfer problem in a simple Markov decision process. In the training task, the optimal policy is the sequence of actions A, B, then C. In the transfer task, the optimal last action switches from C to D. The blue curve represents PPO, an on-policy policy gradient method. The red curve represents CBS, an on-policy single-step temporal difference method. Both have similar learning efficiency on the training task. But when we transfer, PPO is not efficient at all at adapting to the new situation. It converges 3.9 times as slow as CBS on average. This requires explanation. What is the cause of this enormous gap in transfer efficiency? In this talk, I will talk about independent credit assignment, what it is, how it can explain this gap in transfer efficiency, and how it can be used to design and evaluate more modular learning algorithms. We want algorithms that can transfer efficiently by reusing previously optimal decisions for solving new tasks, modifying only what needs to be modified and not modifying what does not need to be modified. We have started with a vague hypothesis, also echoed in the machine learning community, that modularity could enable more efficient transfer. But the challenge to precisely expressing this hypothesis, let alone testing it, is that we lack a precise language for describing what modularity means in the context of a learning system and how it depends on the structure of credit assignment. This is because modularity has traditionally been defined for static systems whose mechanisms are assumed fixed, whereas learning systems are dynamic systems whose mechanisms evolve over time. The problem we face is to extend the static notion of modularity to learning systems and understand its implications for credit assignment, in particular for reinforcement learning. Our work proposes a candidate solution to this problem. My goal for this talk is to convince you that modularity in learning systems requires it to be possible for the credit assignment mechanism to modify the learnable mechanisms independently. Modularity is just as much about independent credit assignment as it is about independent learnable functions. This talk is organized into 3 parts. In the first part, I extend the definition of modularity developed in the causal literature to describe dynamic systems. In the second part, I show that learning algorithms are examples of dynamic systems and propose a test to determine whether credit assignment mechanisms can modify the learnable components independently. At this point, we will be able to test our hypothesis because we now have a precise definition of modularity for learnable systems and a practical criterion for testing whether a learning algorithm meets that definition. And finally, I test our hypothesis on discrete action reinforcement learning algorithms. Let's start with modularity for dynamic systems. We first review modularity for static systems, formalized in the causal literature as the algorithmic independence of mechanisms. We call a dynamic system the process that encompasses a sequence of modification to the static system. Viewing a system along its sequence of modifications then gives us a natural extension of modularity as the conditional algorithmic independence of its mechanisms conditioned on the system's previous state. Here's a causal graph. This is the same graph with the mechanisms that produce each node drawn explicitly. Then modularity of the system has been previously formalized as the algorithmic independence of the mechanisms, meaning that knowing the source code of the program that computes fj does not simplify the program for computing fk. See the paper for more background and explanation of notation. What does algorithmic independence of mechanisms give us? Let's intervene on the graph by modifying one of its mechanisms. Because of algorithmic independence, this intervention does not affect the other mechanisms, even if it affects the nodes. Let's intervene on the graph again by modifying another mechanism and another. Each time we modify a mechanism, we generate a new static system represented by a new causal graph, where the outer process that modifies the causal mechanism is the human. We call the sequence of static systems, along with the outer process that modifies it, a dynamic system, where each time slice represents a different causal graph. Let's unroll the outer process out more explicitly as a dynamic graph, a Markov chain over graphs. Then we can naturally extend the static notion of modularity to a dynamic system as the algorithmic independence of mechanisms, conditioned on the previous graph before the intervention. To recap, modularity has been previously formalized as the algorithmic independence of the mechanisms of a causal graph. A dynamic graph represents a sequence of interventions along with the outer process that performs these interventions. Then we formalize modularity in a dynamic system as conditional algorithmic independence of mechanisms. In the next part of the talk, I show that learning algorithms are themselves dynamic systems, that a modular learning algorithm requires the credit assignment mechanism to produce independent gradients, and that you can test for this property by formally treating learning algorithms as causal graphs and checking for deseparation. Learning algorithms neatly fall into the dynamic systems framework. The causal mechanisms correspond to learnable functions. The causal nodes correspond to their inputs and outputs. Each static graph represents a forward pass of the learning system. Instead of the outer process being a human who intervenes on the learnable functions, the outer process is the credit assignment process of the learning algorithm, which we can split into two parts. The credit assignment mechanism, which takes the previous graph and produces gradients for the learnable functions, and the update rule, which modifies the learnable functions given the gradients. Typically, the update rule is assumed to be a fixed operation, like gradient descent, which factorizes over the learnable functions. The question is, what constraints should the credit assignment mechanism satisfy to modify the learnable functions independently? We show in our paper that it must produce gradients that are algorithmically independent, conditioned on the graph in the previous iteration. Then, if the gradients are conditionally independent, the learnable functions in the next iteration will also be conditionally independent. Check out the paper for our theorem that formally states that a learning algorithm is modular if its learnable mechanisms do not share weights and if its credit assignment mechanism produces independent gradients. But algorithmic mutual information is not computable. We need a practical criterion to design and evaluate credit assignment mechanisms that produce independent gradients. It turns out we can get this criterion by flattening the graph of the learner and the graph of credit assignment into one big graph, where both the mechanisms and data are treated as nodes. Then we can simply test if the gradients are conditionally independent by inspecting the graph for deseparation. They are deseparated if each gradient is produced by a different function. If there's a hidden variable, then the gradients are not deseparated and thus not conditionally independent. This makes intuitive sense because if we want the mechanisms to be independent, there can be no dependency introduced through the causal structure internal to the credit assignment mechanism. Check out the paper for our theorem that formally connects deseparation and independent gradients. To recap, learning algorithms are examples of dynamic systems. If we want the learning algorithm to be modular, then the credit assignment mechanism needs to produce independent gradients to modify the learnable mechanisms independently. By treating the learning algorithm as itself an algorithmic causal graph, we can test for this property without any training by checking whether the gradients are deseparated. At this point, we have developed a language for precisely expressing our hypothesis by presenting a formal definition of modularity in learning systems, as well as a criterion to test for it. In the last part of the talk, we can finally ask whether modularity in reinforcement learning improves transfer efficiency. We first compare major classes of reinforcement learning algorithms on whether they produce independent gradients over a credit assignment update. Then, we empirically test whether having this property correlates with transfer efficiency. We now apply our framework to reinforcement learning algorithms by representing these algorithms as causal graphs. In reinforcement learning, the forward pass of the learner is a rollout in the MDP. When we consider modularity in reinforcement learning, we are interested in the independence of the decision mechanisms that control each value that the action can take on. In this case, there are three possible values of the action variable. Each decision mechanism produces a bid, which could correspond to an action probability or estimated Q value. These bids get filtered by a selection mechanism, such as a categorical sampler for policy gradient methods, or an epsilon greedy sampler or Vickrey auction for action value methods. Since we are only interested in the modularity of these decision mechanisms, we can absorb the other operations into the edges and use brackets to denote that we bundle the states, actions, and rewards together. We have now decomposed the causal graph of a single step of the forward pass of the RO algorithm. Here's the causal decomposition again, shown across time. As before, the credit assignment mechanism is the outer process that produces gradients for the graph. We now analyze the causal structure of the credit assignment mechanism for various RO algorithms. For policy gradient methods, because of the softmax in the policy, the gradients of the decision mechanisms all share a normalization constant as a hidden variable, so the gradients produced are not deseparated. Therefore, policy gradient algorithms are not modular. For n-step temporal difference methods, the gradients all share some sum over sampled rewards as a hidden variable, so the gradients produced are not deseparated, and n-step temporal difference methods are not modular either. This leaves single-step temporal difference methods, which also have an intermediate variable, the TD error. But unlike policy gradient or n-step temporal difference methods, this hidden variable is not shared, because it is only connected to the gradient of the decision mechanism of the action that actually was taken, while the gradients of the other decision mechanisms remain zero. Therefore, single-step temporal difference algorithms are modular when the trajectories are acyclic. See paper for more details. Again, the gradients for policy gradient and n-step temporal difference methods are not deseparated, whereas the gradients for single-step temporal difference methods are in generic cases. To recap, we want to test the hypothesis of whether modularity improves transfer. To do that, we need to determine which reinforcement learning algorithms are indeed modular. To answer this question, we represented reinforcement learning algorithms as causal graphs. We identified that all policy gradient methods and n-step temporal difference methods do not produce independent gradients because the causal structure of their credit assignment mechanisms contain a shared hidden variable. In contrast, in generic cases, single-step temporal difference methods do produce independent gradients and thus are modular. Having identified which RL algorithms are modular and which are not, we now are in the position to test whether modularity improves transfer efficiency. As illustrated by our motivational example, we are interested in transfer problems that require only sparse changes to a sequence of previously optimal decisions, because that tests to what extent an algorithm can separate what needs to be modified from what does not need to be modified. We can represent this kind of transfer problem as a simple MDP. Circles represent states, edges represent state transitions. Here we label some transitions with the actions that cause them. We have a start state and a goal state. During training, the optimal decision sequence is A, B, then C. To generate the transfer task from the training task, we modify the transition that B corresponds to. Now the original sequence of decisions is suboptimal. But swapping action C for action D in this case is now the optimal thing to do. Our MDP has 6 possible values for the action variable, so we will have 6 decision mechanisms. Similar to how analysis of D-separation is conducted with triplets of nodes, we enumerated all possible topologies of triplets of decisions, and for each topology, we generated 3 transfer tasks by enumerating all the ways of making an isolated change to the optimal decision sequences. This includes our motivating example, where the last action should change from C to D. We compare 3 algorithms: the cloned Vickrey society, or CVS, which is a modular algorithm; PPO, which is not modular because the policy is not factorized along the actions and its gradients are not independent; and PPOF, a variant of PPO with a policy network that is factorized over the action variable. PPOF is also not modular because its gradients are not independent. We chose PPOF as a baseline because while it is intuitive how network factorization contributes to modularity, comparing CVS with PPOF specifically tests the role of independent gradients and enabling transfer efficiency. When we consider all 9 transfer settings across the board, CVS is consistently more sample efficient in the transfer task, despite having comparable training efficiency in the training task. Thus, we have tested our hypothesis and it survives the experimental test. Modularity does seem to correlate with improvements in transfer efficiency. We dove deeper to find an explanation for why this hypothesis seems to hold. We measured the outputs of the decision mechanisms and observed how they change between training and transfer. These outputs are the bids. The higher the bid, the more likely the action for that decision mechanism will be selected. Here we see the bids for action C both drop because they are suboptimal in the transfer task, while the bids for action D rise because it is now the new optimal action. Notice how much faster CVS in red switches compared to PPOF in blue, possibly because the decision mechanisms of CVS can be adjusted independently, whereas for PPOF, they are tied together by a softmax. Actions A and B are the optimal actions at states 0 and 1, and we see that both of them get affected by the transfer task, but CVS recovers much faster than PPOF. To conclude, we started with the hypothesis that modularity improves transfer, but we had to build up some formalism to even get to the point where we could test this hypothesis. First, we had to extend the definition of modularity developed in the causal literature to describe dynamic systems. Then we connected learning algorithms to causal graphs and proposed how to test whether the credit assignment mechanism can modify the learnable components independently. Finally, we applied this framework to determine which RO algorithms are modular and showed that the hypothesis survives a suite of empirical tests. What we learned from all of this is the following takeaway message. To build learning algorithms that transfer efficiently, we need independently modifiable components. To get independently modifiable components, we need a credit assignment mechanism whose causal structure makes independent modification possible. I would like to thank my collaborator Sid Kaushik and my advisors Sergey, Levine, and Tom Griffiths for supporting me through this very fun project. Check out our project website for more information.